Well, thank you, Morten. We will dedicate the last part of the webinar to ASK's inorganic binder system called INOTEC. The binder system is applicable in hotbox core production processes and has set an industry standard as the emission-free alternative binder system in comparison to conventional organic binder systems, especially in the light metal automotive industry and low-pressure die casting and gravity die casting applications. The INOTEC technology is described as a two-component binder system. Component 1 forms the liquid INOTEC binder, which can be described as a modified solution of alkali silicates. The binder has a strong influence on specific properties of the molding mixture, for example, flowability, and the core itself. Characteristic strength profiles with adjustable humidity resistance properties result in dependency of the type of product used. Component 2 is the powdered INOTEC promoter, which is a mixture of synthetic and natural raw materials based on a completely inorganic product composition. Through the use of the INOTEC promoter, primarily mechanical and thermophysical parameters during the core production process, but in particular during the casting process, can be adjusted to assure castings of high dimensional accuracy and high surface quality. The main function of this component is to increase immediate core strength for fast ejection in the core production process. A typical molding mixture based on silica new sand is composed of approximately 2% of the liquid INOTEC binder and 1.0 to 1.9% of the solid INOTEC promoter. The higher the addition rate of the promoter, the higher the performance level of the product. The resulting molding mixture is fluidized by compressed air and transported to the cavity of the core box via a cooled shooting plate with integrated shooting nozzles. High diameters of the shooting nozzles and temperature control of the shooting plate are fundamental to assure high productivity in the production and sand cores of high quality. The shooting plate shuttles aside and is simultaneously substituted by the gassing plate. The core production is characterized by a physical chemical curing mechanism. The introduction and supply of thermal energy from heated steel tools and dehumidified heated compressed air leads to the evaporation of the free solvent water and simultaneously initiates a chemical polycondensation reaction with the formation of a three-dimensional silicate network that describes the axial strength composite in the sand core. The 100% emission-free footprint of the INOTEC technology can vividly be demonstrated best by comparing the formation of fumes and smoke as a result of the thermal pyrolysis of the binder system upon casting at the raw part in the process of permanent die mold ejection. The picture on the left shows a polyurethane cold box bound core package after cylinder head casting directly at the ejection process of the permanent die mold. The formation of pyrolysis products visible by fumes and smoke leads to the necessity to implement exhaust air treatment systems. The picture on the right shows the exact same casting process with a slight but very important difference that the INOTEC technology is used. In comparison, the formation of pyrolysis products from the binder system is completely absent. The INOTEC binder system is only dehydrated and converted to a glassy state by thermal strain of the casting process and remains inside the sand cores. A gas chromatographic analysis of the emission stream shows that 98% of the emissions can be reduced. The main improvement here results from the absence of medium volatile compounds, which are responsible for BTX emissions in the casting process using polyurethane standard cold box binders. Besides the ecological benefit of missing emissions in the casting process with INOTEC, savings in cleaning maintenance for the permanent die mold are a result as well. When casting with organic sand cores, the buildup of condensate occurs on the permanent die mold, which must be removed by employees in regular intervals to ensure correct functionality, especially of movable parts. The physical strain for employees involved in this work is high. In addition, there's a very high level of noise pollution. When casting with inorganic sand cores, this costly and energy-intensive cleaning step is reduced by more than 50%. As a side effect, permanent die mold casting processes with inorganic bound sand cores are operated at lower temperatures compared to casting processes with organic bound cores, leading to a higher die mold availability of 25%. Furthermore, the time-consuming cleaning of the air systems is no longer necessary. The use of hazardous substances in the exhaust air purification system is also no longer necessary. The figure here summarizes the comparison of CO2 equivalents for different binder systems in an automotive light metal foundry normalized to cold box for permanent die mold applications. The lack of dry ice usage in the cleaning process and the lack of energy consumption for the air treatment systems in case of INOTEC leads to a considerable decrease in the CO2 footprint for INOTEC. Conventional hot box binder systems based on organic components show an even higher CO2 footprint than cold box. ASK Chemicals commissioned TÜV Rheinland to create a comparative environmental life cycle assessment of a standard cold box binder system with INOTEC in order to clarify which product is more environmental friendly through the respective life cycle. Overall, the inorganic binder system INOTEC fares better, leading to the conclusion that INOTEC is an eco-friendly product and is more environmental friendly than the compared cold box system. Besides the ecological benefit of meshing emissions in the casting process with INOTEC, an increase in productivity is apparent as well. The lack of condensate buildup in the permanent die mold for INOTEC-based casting processes enables lower die mold temperatures, thus faster solidification results in addition to a higher permanent die mold availability because of savings in maintenance and cleaning. These effects overall contribute to a productivity increase of roughly 30% in the casting process at the die itself. An additional advantage of the inorganic binder technology INOTEC is embedded in its technological influence on the metallurgic structure of the casted aluminum parts. The metallurgic property of secondary dendritic arm spacing is mainly influenced by solidification. Thus, faster solidification leads to lower secondary dendritic arm spacing values and castings with higher mechanical strength. Lower permanent die mold temperatures in case of INOTEC already provide faster solidification. But the residual water of the inorganic binder bridge further withdraws energy from the liquid aluminum melt for evaporation, leading to an add-on effect on solidification. Inorganic sand cores exhibit roughly 25% of the gas potential of organic bound sand cores. Thus, the core percentage in the casting and degree of porosity is dramatically decreased. Both parameters contribute to improved dynamic properties of the casting as metallurgical structures of higher strength and elongation properties result. This effect enables wall thickness reduction and contributes to the overall trend of downsizing and lightweight construction, especially in ICE powertrain applications. Traditionally, the inorganic binder system INOTEC has been utilized in low-pressure die casting and gravity die casting processes to produce classic ICE powertrain components, for example, 4 and 6 cylinder heads and the corresponding crankcases. Nowadays, INOTEC has matured to a much more versatile binder system, which is applied to a wide range of aluminum passenger car components, for example, e-engine housings, suspension parts, and body structures. The difference to state-of-the-art ICE powertrain applications is characterized by a different number of cores per core package and varying core weights. While ICE powertrain components are based on core packages with different cores of high diversity concerning mass and geometry, suspension parts and body structures casting processes are based on just 1 or 2 cores with greater mass. The versatility of the INOTEC technology is achieved by segmenting the necessary product performance requirements of the binder system by the castings produced and by considering the total cost of ownership approach that captures the full cost structure of a casting process until selling the part to the respective customer. The determining key performance indicator is the so-called sand-aluminum ratio that compares the weight of the sand core package with the weight of the casting. The higher the KPI, the higher the sand core weight is and the lower the casting weight. ICE components, for example, cylinder heads and crankcases, show a very balanced sand-aluminum ratio, while the ratio value is already increased for e-engine housings. Both casting types need in general binder systems that ensure high dimensional accuracy, as well as sand cores with a low gas potential and a very good shakeout performance of the cores, as both components rely on filigree water jet components, geometries. In comparison, suspension part castings are produced using voluminous sand cores, thus the sand-aluminum ratio is higher, and the main product focus changes to cycle time, strength, and core distortions, all parameters of the core production process. The following 2 slides will be used to demonstrate the effectiveness of this approach. A predominant problem area in the production process of cylinder heads using inorganic binder systems is the appearance of sand adhesions and penetrations after raw part machining, especially on the core print areas of the port cores. This defect is described by the partial appearance of sand grains on the casting surface due to the mechanical penetration of the liquid melt into the sand core surface or the electrostatic adhesion of sand grains on the casting surface itself. Casting parameters, for example, casting temperature and pressure, have an influence, but customers are seeking for a chemical binder solution that withdraws the need for intensive process control and casting rework by shot blasting. In this case, ASK is able to fine-tune the performance properties of the INOTEC promoter to the local sand quality used. As the components of both silica sand and the promoter are of inorganic nature, an interaction is commonly observable and changes the properties of the sand core, for example, the property of thermal stability. Thermal stability describes the resistance of a sand core towards thermal and mechanical strain of the casting process, and it is an intrinsic property of the binder system itself, characterized by the so-called softening temperature. The softening temperature of a binder system can be monitored using the heating microscope technology. The specimen on the left here shows a low thermal stability and is softened at temperatures below 730 degrees, the casting temperature of aluminum melts. The sample on the right exhibits a high thermal stability and softened outside the temperature range of aluminum casting applications, and the specimen remains stable over a wide temperature profile. The result of customizing the thermal stability of the binder system to the impurities of the local sand quality is that the defect of penetrations disappears and withdraws the need for cost-intensive shot blasting. The second example arises from the field of suspension part castings. The customer reported a limitation in productivity due to long cycle times and the reduced tool availability in the core shop. The current addition rate of the inorganic binder system was in principle too high, but necessary to handle voluminous cores because of strength. The buildup of binder system residues on the core box surface and the core itself resulted in an excessive use of release agent and tool maintenance work in short intervals. The solution here is to customize the binder system to the process by providing a binder system with an adjusted strength profile. Inorganic binder system for suspension part cores need an adjusted strength profile in comparison to cores for cylinder head castings or crankcases. Higher immediate strengths are necessary, lower final strengths are acceptable. As a result, the components of the binder system could be reduced, enabling a cycle time reduction by 10%. In summary, the INOTEC Trinity concludes the ecological, economic, and technological benefits of the binder system. INOTEC is clearly an emission-free alternative to conventional organic binder systems like cold box, more suitable and more environmental friendly. The initial higher invest for the equipment of core manufacturing is compensated along the process chain by savings in maintenance, the lack of air treatment systems, and the higher productivity at the die. Technological benefits rely on improved dynamic properties of the casting, enabling downsizing and lightweight construction. INOTEC is able to reduce both VOC emissions as well as BTX emissions by up to 98% along the complete casting process chain and is your industry standard for emission-free applications.